As you have understood the basics of digital elevation model, now we will talk about the spatial data interpolation, or how we actually make the surface models. So what is data interpolation or spatial data interpolation? So when we're talking about data interpolation, we're actually talking about a procedure to predict values of attributes at unsampled points. So in bathymetry or in hydrography, normally the attributes are depths, but sometimes it doesn't have to be depth. It could be the rainfall, it could be maybe temperature or something like that. So for example, we've got some attribute that we didn't know. In the California, we only have this many sample points, and we can actually make a surface, or basically an interpolated surface, by doing the interpolation of the sampled points, and then we will have this kind of map. So why do we have to do spatial data interpolation? Because sometimes we cannot measure at all locations. So we have many methods to do this. The first one is basically you need to understand that each method combines information about the sample coordinates. So basically coordinates is your X and Y coordinates, and the magnitude of the measurement variable, for example, depth. And then each method differ in weighting and the number of observations that are used. And of course, there is no single method that has been shown to be more accurate in every application. So it really depends on which method suits best to your interpolation methods, and then you can see how good it is. So basically, it's kind of a trial and error sometimes. So you can try to interpolate it, your data with several different methods of interpolation, and you can compare and actually decide which one is the best for that data set. So we will talk about some examples of the interpolation methods. The first one is called the inverse distance weighted, or the IDW. So the IDW basically estimates the values at unknown points using the distance and values to the nearby known points. So the weight itself is basically the inverse proportion of the distance. So basically, if we've got this is our interpolated point, and these are our data. Okay, so if the distance between these interpolated points, remember that in IDW, that's basically the gridded one. So you can imagine that this is your grid, okay, and those are basically your data. So we want to know the value in this grid. So we can interpolate at the point based on the closest observed point. So we've got three closest points in here, which is 30, 50, and 52. And the closest one is actually the 30. So the 30, it has kind of the weight of 2 because it's the closest one. But basically not 2, it's 1/2, as you can see. And then the distance between this and that is actually, for example, 6. So the weight is actually 1/6 because we want to trust the closest one compared to the further one. So this actually should be used when the set of points is dense enough to capture the extent of the local surface variation. And this is basically a sample of how it works. So you can imagine that basically the further it is, it will actually count it as less weight. But the closer it is, then you will have it as a better weight. In Kriging, that's a bit more complicated because it has a statistical analysis behind it that looks at spatial trend and the random variation of the sampled surface. We will see how it actually works. And the sampled points, so for example, you've got a lot of points, right? But you actually, in Kriging, they only take a number of points sampled, and then they will make like a variogram. And this variogram model will then use to interpolate the entire surface. So if you can imagine that, for example, the same thing, so we're going to interpolate Z1, Z2, and Z3 into Z4. we've got something that is called the lag distance. So the lag distance is, for example, this is the lag distance between the two, this is the lag distance between the two, etc. And then we can actually compute the semi-variance of the area, for example, between Z1 and Z2. The semi-variance would be, that's your Z, and then that's another Z, and N then would be, N would be 2. And then you can actually compute your semi-variance in here. But for example, if you want to make it here, then you will have Z4 minus Z2, you will have Z4 minus Z1, and then Z4 minus Z3, and the N then would be 4, for example. So basically, you will have a graph of the lag distance, that's the blue one, compared to the semi-variance that you computed, okay? And then you will basically make a fit model from your actual plot. So it's quite complicated, but don't worry about it because basically this is the idea of what is behind it. So what I'm going to say here is that compared to IDW, the kriging will actually make the surface more smooth, as you can see in here. So if you compare the surface to the surface that we had earlier, you can see that the variation in here is really, really small because everything in here is kind of average. You can say that. Okay, so that's kriging. And then we've got spline. So in spline, actually, we are basically trying to make a smooth surface that curves through points. So for example, you can imagine that we've got a paper. We've got a paper, maybe I'll have a small paper in here. So within the small paper, you're trying to actually bend this paper based on the depth or the height that you've got in each point of the sample. So for example, if you've got a deep one in here, you will bend it like that, and you have a high one in here, then you will bend it like that. So you basically have a surface, a continuous surface that is bent at the points that are sampled. So it will basically try to force a smooth line to pass through a desired sample of points. So for example, if this is your surface model, and then we will cut through this, this is how it will look like in one line. And this happened in each of the lines. So you will have basically a very, very smooth line as well, but not as smooth as the kriging because you don't have the calculation of these semi-variance and whatever. It's just basically, okay, that one is high, that one is low, just like that. And then it basically constructed from a set of joint polynomial functions. So you can say that this one is, okay, there's a polynomial function to do that, and there's another polynomial function in that, there's another polynomial function in that. So it's actually a lot more, well, a lot less complex than what we had in kriging. So this is how the surface looks like. So it's still very, very smooth, but as you can see, there's a lot more variation in the surface or in the height compared to what we had in kriging, for example. And the spline, actually, you can vary the surface tension or something that is called T. Sorry if my face covers this bit, but basically, you can set how variative your surface would be based on the tension. For example, if the tension is only 20, the tension is basically like how if you're imagining your surface as like a rubber band, or not a rubber band, a rubber sheet. If you've got a tension of 20, then you actually have very, very small tension, or like you pull your rubber sheet very, very small. Okay, so you don't really pull it with your whole strength. It's just like 20. But if you increase your pulling strength, or if you increase your tension into 50, for example, as you can see, the variation is less than this one, right? So it's actually less because you're actually pulling it away strongly. So you will have this kind of thing. And if you increase it more, then you actually only have a very, very small variation, as you can see, but you can you can see clearly where your points are, and it doesn't really look good. So when you're applying spline interpolation, you need to have like a sense of if you know a sense of physical, like a physical sense. Does it make sense, or do I need to pull my rubber sheet maybe stronger, or do I need to release it a bit, stuff like that. And the last one that we're going to talk about is the natural neighbor. So it's a bit different from the others because, as you know, the others are grid-based method, but in natural neighbor, it's not grid-based. So we will basically find the closest subset of input samples and applies weights to them based on proportionate areas. So it works a little bit the same with the inverse distance weight, but you don't make a grid out of it. I will explain it later. So it only use a subset of samples of the points. So you will not have, because it's not, again, it's not gridded. So on the other samples before, you will make a grid, and then you will basically try to interpolate everything. So you will have actually a grid of like a rectangular grid. But in natural neighbor, for example, your number of samples look like this, then your interpolated surface will basically look like this. So it will only use all the samples within its range. So it will not, for example, interpolate, or basically it's not interpolate, it's extrapolate outside of the zone. So those things will not exist. So it works actually very, very well with clustered scatter points. So for example, even though it's closed by my drawings, but you will see what I mean. So for example, you've got this set of points surveyed from the field. The first thing you want to do from here is actually make kind of an irregular grid, I would say. So you can see how it looks like as this one, this area is very, very dense, then your grid will be dense in here, but outside it's going to be less dense. So that's basically how it looks like in the outside, okay? So from there, you will basically try to, for example, how do you actually put a number on this? Is basically try to see the distance from here to the closest irregular grids, okay? And then afterwards, you will see, you will have something like that, okay? So for example, this one is actually very, very close. So you will have this one as a bigger weight. And then this one is also close, so that's a bigger weight. And then this one is also close, then that's a bigger weight. But this one is actually not that close, so the weight is going to be very small. This one is also not that close, and this one is still close, but not as close as this one and that one. And this one is not close. So that's going to be your new depth grid, basically. And the result will be irregular again, because it's not a gridded one. If you remember, the other ones kind of look like this. So it looks like a rectangular or a square grid. But here you've got something like this, because again, it will only calculate within the range of the samples. It will not extrapolate. It will not count something that is, outside of the sampled zones.